Hi, this is Doğan Shintuna. Today I will present our paper named as a variable-fractional order admittance controller for pHRI. I would like to note that this study is supported by the Scientific and Technological Research Council of Turkey. In this study, we present a new variable-fractional order admittance controller for physical-human cobot interaction. Our application is collaborative drilling. We show that our controller outperformed the alternative admittance controllers existed in the literature in task performance. Now I introduce our setup. We used KUKA-EVA as a cobot and we strictly attached a drill to the end effector of our cobot. During the whole task, the cobot was programmed to constrain the movements of the participant along the direction perpendicular to the surface of workpiece. In our study, we chose wooden strand board for drilling. Additionally, in this study, we utilized an augmented reality interface to inform user about task details. Force sensors were used to measure human force and interaction force. In these videos, you can see our collaborative drilling task. The left video corresponds to view of augmented reality interface and the right one is recorded using an external camera. First, the operator approaches the workpiece and the drilling process starts. The operator is asked to penetrate 5 mm into the workpiece. You can see that in the left view, the operator can see his drilling depth on the fly. In addition to this, blue bar also informs the operator about the drilling depth. So, what is the main problem in this collaborative drilling task and what we are trying to solve? Our main goal is to create a stable and transparent operation. However, robust stability and transparency have a contradicting nature. This creates a trade-off between them. Robust stability requires conservative approaches and they degrade the transparency. On the other hand, transparency is needed for quality of interaction, so we need to balance this trade-off between stability and transparency. In our task, transparency is mainly needed when the operator approaches to the workpiece. This part can be considered as a free movement. However, when the contact occurs during drilling, the system must be stable for safe operation. In order to reach our goal, we focused on the controller of our cobot. In this study, we propose a variable-fractional order admittance controller in order to balance the trade-off between stability and transparency. You can see our control architecture in here. In this architecture, we focus on the design of the admittance controller. The admittance controller takes interaction force as an input and generates reference motion command for the cobot. Then the cobot tries to follow this reference motion command. After that, the environment and the human operator generates an interaction force. Then this closed-up architecture repeats itself. Now I will explain what fractional order admittance controller is and how it differs from integer order admittance controller. Let me give you a brief background information regarding admittance controller. As I mentioned earlier, admittance controller generates the reference motion command for the robot based on the external forces. A standard admittance controller that mimics the behavior of a mass damper system is widely used. Here the idea is that if this force was exerted to this mass damper system, what would be the velocity of the mass? Then this velocity is fed to the robot. As you can see here, a standard mass damper system is utilized as an integer order admittance controller. Recently, it was shown that one can take the advantage of fractional order calculus and control systems and use a fractional order integrator in the admittance controller. Here, alpha is the fractional order. The mass and damping contributions of the controller changes depending on alpha. Note that when alpha is equal to 0, the behavior of the controller approaches to that of pure damper, whereas the controller becomes equivalent to an integer order admittance controller when alpha is equal to 1. As you can see, when alpha takes a value between 0 and 1, this fractional order term can add very important characteristics to the controller. Specifically, the mass and damping contributions now become frequency dependent, which was not the case with an integer order admittance controller. With this feature, for different operating frequencies, different mass and damping contributions can be provided. What is the advantage? With the fractional order admittance controller, at low frequencies where intentional movements occur, energy dissipation capacity can be kept low, which leads to a better transparency. At high frequencies, where noise and modeling uncertainties danger the system more, robust stability is needed. So, high energy dissipation capacity at high frequencies under fractional order admittance controller is advantageous. So, we can say that fractional order admittance controller can provide better stability, robustness, and transparency. In this study, we further exploit the advantage of fractional order admittance controller and propose a variable fractional order admittance controller which is based on the adaptation of the order of the integration. In particular, we change fractional order in the controller for our needs. In our collaborative drilling task, in the driving phase, we need the robot as transparent as possible, since there are free movements in this phase. However, in the penetration phase, contact occurs, and we need to ensure the stability of the system. So, we decrease fractional order of the controller linearly in order to increase effective damping monotonically as the tooltip gets closer to the contact point. You can see here the change of fractional order with normalized distance to the workpiece. You can find details of the parameter selection criteria in the paper. In order to show the advantages of variable fractional order controller, we compare our controller to a standard integer order admittance controller with fixed parameters and variable integer order admittance controller during our collaborative drilling task. In the fixed integer order admittance controller, mass and damping parameters do not change throughout the task. However, in variable integer order admittance controller, mass and damping terms change during the task. Recall that the mass and damping contributions under fractional order admittance controller are frequency dependent. So, for a fair comparison with variable fractional order admittance controller, we need to come up with a common ground for these controllers. To this end, we use the admittance matching technique. With this technique, we can match effective mass and damping values of fractional order and integer order admittance controllers for a specific operating frequency, so that for this specific frequency, their behavior becomes equivalent. In our case, we match this effective mass and damping terms at operating frequency of our drill using these equations. The change of controller parameters can be seen in here. The main goal of our experiment is evaluating the performance of these three controllers. In order to do that, we compare them in a collaborative drilling task. Our experiment can be categorized in two phases: driving phase and penetration phase. In the driving phase, human operator approaches the wooden workpiece to drill. This part requires transparency. In the penetration phase, drilling occurs, and the system must be stable to ensure safety. The experiment was conducted with 7 participants. Each participant performed a total of 15 tries, 3 interaction controllers and 5 repetitions. To note that the participants were asked to penetrate into the workpiece to drill a hole with a depth of 5 mm. Visual information displayed to the participants through the augmented reality interface during the execution of the drilling task. In the driving phase, distance to the workpiece was displayed, whereas the current drill depth was displayed during the penetration phase. The green circle in the view indicates that the robot controller is active. The red and white bars represent the cross-section of the workpiece. The red bar shows the part which should not be penetrated, whereas the white bar shows the desired depth that will be drilled. The blue bar grows from right to left as the drill bit penetrates into the workpiece and shows the current drill depth. In order to compare controllers, we defined several performance metrics related with our experiment. First of all, we compared the total effort by participants under 3 different controllers, and results show that they put significantly less effort throughout the drilling process under variable fractional order admittance controller. When we investigate force applied by human during the driving phase, it can be seen that under variable fractional order admittance controller, participants applied less forces. However, they reached higher velocities despite applying low forces under variable fractional order admittance controller. Hence, participants completed the task faster, though there were no instructions to do so. In addition to all these improvements regarding transparency, variable fractional order admittance controller did not compromise stability or accuracy. The difference of amplitude of oscillations under the tested controllers was not significant. So, it means variable fractional order admittance controller provided comparable attenuation for the drilling-related vibrations. Moreover, the accuracy in drilling depth was similar to that of the controllers. These results indicate that variable fractional order admittance controller improves the quality of the interaction at low frequencies where intentional control takes place while not compromising from stability robustness. As a conclusion, in this study, we proposed a variable fractional order admittance controller for physical human-robot interaction systems and evaluated its presented advantages over variable and fixed integer order admittance controllers, where all the controllers were designed using admittance matching technique to display similar stability robustness against the undesired effects disturbing the system. The proposed variable-fractional order admittance controller outperformed the alternatives in terms of task performance. So, the proposed variable-fractional order admittance controller can offer a better compromise between stability, robustness, and transparency than alternatives.